Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
Yep, that's us. Hi, everyone. I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a friend to the universe who was clearly unprepared in that moment.
It's
You
fine.
caught me by surprise, bestie.
I sure
Who are
did.
you?
I just walked into your office. Hello, my name is Connie. I am a friend to the universe and a friend to Moiya and someone who just likes to barge into her office every so often. So that's my bad. But I thought, it was the time to start, and I just didn't consult with her on whether or not we were ready. It's cool. Don't worry about it.
You're one of the few people who has an extra key to the office anyway.
Yeah,
so
I'm very privileged.
But you know how easily startled I am.
Yes.
That's just a me thing.
I know it's late, and that was my bad. I should have was loud. Should have been louder on my way in.
Mm-hmm. Well, I was just so engrossed in thought about infrared light, and I'm actually glad you're here so we can talk about it.
Wow, how fortuitous for me to walk in at this very moment.
Well, I'm always thinking about something.
That's true. So I love to just barge in and be like, Moiya, what are you thinking about right now? Let's talk about it.
That's a great device. We should use more.
So what about infrared light? What are you thinking about?
Well, I was thinking about this connection that it has to heat and how that seems to be very important to a lot of what we know about it and its discovery in the first place. Because we don't associate any other region of the electromagnetic spectrum with heat, even though technically all electromagnetic radiation is energy, which is heat. Mm-hmm. It is the motion of molecules, so it is temperature. But it's just like this interesting, weird little consequence of how our solar system is set up that makes it so that we associate infrared with heat as humans.
Yeah, it reminds me of when you were telling me about the electromagnetic spectrum and how, I forget his name, but someone who was discovering the differences between them was doing that temperature test. And
Johann Ritter.
Yeah, yes. John Ritter's great-great-great-great-great-grandfather. Yes. How could I forget? And how he tested ultraviolet and then the infrared, and the infrared was warmer?
He did not do the infrared.
No? Oh, I remember that wrong.
It's okay. You got most of it.
Yay.
I'm very proud of you, bestie.
Yay.
So Johann Ritter's, Johann's experiment actually came after William Herschel's experiment, which came after Isaac Newton's experiment. So Newton was the first to write about light being split up into its different wavelengths through a prism. And then in 1800, William Herschel takes this Isaac Newton experiment of splitting light up into its different wavelengths, and he puts thermometers in the different color bands because he's noticed that it gets warmer as you go towards the red, which is interesting, right? Because we would think, or I would think, that it's the opposite because blue light is more energetic than red light. So
yes, and blue
I would
flame
expect the blue
hotter than red flame.
Yes, but the prism scatters the blue light more than it scatters the red light. So it's almost like the red light is ultra concentrated and the blue light is kind of diffused after it goes through the prism. And that means that you're getting like more energy in the red and even more in the infrared, because William Herschel puts this extra thermometer right on the other side of the red light and notices that it's even warmer than red. And that is infrared. And then Johann Ritter kind of like bit on this, and that's why he discovered ultraviolet in 1801.
Right. Okay.
But even before that, there was this knowledge that like light can be associated with heat. People understood that fire, even on the parts outside of the hot parts of fire that you can see, you can still feel it, right? Like that's why we have fire. And in 1681, it was a French physicist / priest named Edmé Mariotte who showed that glass would let light through from the sun, but wouldn't let ambient heat from sunlight through. So clearly there's this difference between visible light and the hot light, the heat light. So that was before William Herschel discovered infrared, but that kind of connected some dots there.
Yeah, because isn't the glass a prism? No.
Not necessarily, but
Right.
prisms can be
glass.
are
Yeah.
usually made of glass. Yeah.
Right.
But like a window wouldn't.
Right, because I was like, yeah, it's not as sophisticated as maybe now. We have like the insulated and all this stuff, so it like helps. I'm thinking about like UV rays coming through the window and how we like filter it out in the ways that they try to.
Yeah, you can put special coatings on them, but glass is also pretty effective at filtering out the UV rays. At least not all of them, but a lot of them.
Nice, that's great.
And so that was the discovery of infrared light. We now know that it is on the longer end of optical. So we have visible light in the middle of the spectrum, or optical light, and then infrared is the region that's like just outside of that in the long wavelength direction. Longer wavelengths, but lower energies. And the wavelengths you can expect for infrared light are between 700 nanometers and 1 millimeter. So if anything is a micron or a micrometer, that's in that range, that's infrared. And so it's basically, I was looking for things that are about 700 nanometers across, like smoke particles are apparently like that, tiny. And then on the upper end, about 1 millimeter, you're looking at like a sesame seed.
Oh. What do you mean?
I mean that the distance between each peak as the light wave is traveling forward, that is between 700 nanometers and 1 millimeter. So like there's a range of possible energies here. So like the lowest energy infrared light has the longer wavelengths of about 1 millimeter.
Okay.
Which is still really close together. And then the opposite, it can go down to like 700 nanometers for the really highest energy infrared waves.
Okay, yes. I had to remember the wave part and not just the point, if you know what I mean.
Yes. Well, if you are thinking about the point, I didn't write this down. Having done a lot of my work with radio astronomy, I tend to think in wavelengths. You can also think in frequencies or electron volts, so like an amount of energy. And I think if you were dealing with the specific photon, then you would give its energy value.
Okay.
If you think about it, that's actually a very tiny range of wavelengths, but it does cross several orders of magnitude, from nanometers through micrometers up to millimeters.
Yeah, smoke particle to sesame seed is very big, because I'm like, a sesame seed is pretty big.
Like, you can see
when
it,
you think, yeah. I'm just
It's trapped in your teeth.
Yeah, that's what freaked me out. I was like, a sesame seed.
I know. Wait until we get to radio waves. Ooh.
Oh, I'm scared.
But they are split into different regions. There's the near infrared, which is right by the visible, and then mid infrared. Then there's a little section that astronomers and earth scientists care a lot about called thermal infrared, and then the far infrared with the really long wavelengths or low energies. The thermal infrared have like long or intermediate wavelengths, about 8 to 15 microns or micrometers, and that is purely because everything that has energy, like everything that exists, it emits light, and that light is energy or heat. But the wavelength of light that you emit depends on your temperature. If you have a higher temperature, then you will emit shorter wavelengths of light, like higher energy stuff. Things that are around our body temperature and like normal Earth temperatures, they will re-emit in the infrared. So that's why we think of infrared as hot, because even though stars are way hotter and they shine in the ultraviolet or X-ray or whatever, like a hot day on Earth is going to shine in the infrared. It's just so anthropocentric. It's so nice. And if you get hotter than that, then the object will start shining in a way that we can see, and that's called incandescence. That happens a little bit shy of 1,000 degrees Fahrenheit. So out in space, if we can see the object, that means it's hotter than 1,000 degrees Fahrenheit. And like a lot of the stuff is. All the stars are. But there are a lot of things that are cooler than that. And so we can study them in the infrared.
Okay. Yes.
But that doesn't mean that visible things aren't producing infrared light. our sun is producing a lot of infrared light. About half of the sunlight that actually reaches the surface of the Earth is in the infrared. Our atmosphere also produces a lot of infrared light because it's hot. Like it's just that temperature. So, and stars emit in all of the different wavelengths. They have this continuum of radiation. So other objects will produce infrared light, and we can just use it to our advantage when we are trying to observe cool stuff or cold stuff.
How does it advantage?
The cold objects will shine in the infrared, but not in the visible. The hot objects will shine in all of them, but especially the visible or the X-ray. So you can kind of like remove those hot, shiny objects once you have both images.
Gotcha. You need both to filter out.
I mean, you don't need both. The cool objects shine brighter in the infrared than the other objects do. So the other, it's like flipped. If you were staring in the infrared, things that are invisible to us because they're so cold, they appear very bright. But things that are very hot, they appear dim because they're giving out some infrared light, but most of their light is like X-rays.
Okay. Yeah. It is easier to see in the infrared.
If you are looking at a cool object.
Right, yeah.
Cool, like cold. And that's why we can use infrared for night vision. That's one of the major Earth uses for infrared light. It doesn't even need to be like a you don't need to do anything special to it. If you have an infrared filter that's just letting in the infrared light, objects that are around 100 degrees, they're going to be really bright. And objects that are hotter or colder, they're like not going to show up as much. So that's all night vision is, or thermal vision or heat vision.
Oh. Huh. Oh.
That was many like waves of realization. What happened?
Yeah, I was thinking about videos I've seen that use night vision and how the image appears, and thinking about like a human body. Like if you see a person, their eyes are really bright in the image. At least I can't remember if I'm remembering that correctly, to be honest. But I was just trying to like compare it to like night vision, like video I've seen, and like I don't, it's like your eyes do that like cat-like thing in night vision anyway. I was just trying to compare it to what I've really seen and how the images come, but I'd have to look it up again to compare to this new information.
Yeah. And once you have the infrared light, obviously you can put different filters over it. That's why night vision goggles, like they look green, and heat vision, it looks like the reds and yellows and purples. Like they're taking in the same. Maybe they're taking in near infrared versus far infrared or something, because there's a whole range. But they're taking in infrared light and then figuring out how to display that information to you.
Right.
Another use of infrared light on Earth is heat lamps. And they work the same way light lamps do. You have a filament and you pass electricity through it. If it's a really high resistant filament, then the resistance will produce heat. And they just choose a filament that produces a lot of heat and not a lot of light, because they've experimented and they know that they will react to resistance, electrical resistance, differently. And then another is remote controls and like remote sensing things. Although you can do remote sensing in radio wavelengths, microwaves. You could also do remote controls in other wavelengths too. But typically we will have remote controls around 940 nanometers. So like the pretty small end of the infrared range. I guess that's near infrared. And they use infrared over the other regions because it's very energy efficient, while also not being able to pass through a lot of materials. So it won't pass through a wall and affect a sensor in another room. And the way they work, like your remote control to your TV or something, the way it works is that each button you press will encode a message in a packet of light. It's almost like Morse code with light, but more complicated. And that message gets transmitted to a receiver in your TV or your radio or whatever, and it decodes the message and carries out the command.
Wow.
All at the speed of light.
That's crazy. So I'm pressing the remote and there's just like light literally moving through the air.
Yes. And there always is.
There always is.
But you don't always get to control the light moving through the air, so that is fun. And then a fourth good Earth use that I want us to do more of is renewable energy. Back in 2014, engineers at Harvard proposed that you might be able to capture infrared radiation from the Earth at night as it's re-emitting the heat that it gathered during the day. And then in 2022, engineers at the University of New South Wales in Sydney, so in Australia, they did like the hardware version of this, where they were successfully able to convert infrared thermal energy to electrical power. So they made the emissive energy harvester that the 2014 engineers had talked about, and they are now able to produce power from thermal energy, taking advantage of the difference in temperature between the surface of the Earth and space around us. And when you have differences in temperature, you have a flow of energy, because energy will flow from hot to cold, and a flow of energy can be transferred into power.
Whoa. But that's different than how like solar panels work.
Yes, bestie. But this would give us a way to collect natural energy day long. Because we would collect solar energy, but still some of it would like get absorbed by the planet, and then it would get re-emitted at night, and we would trap that too.
Gotcha. And that doesn't affect... How does it affect the, atmosphere? No? Okay.
By the time it gets to the atmosphere, I don't know. But it's not like we would have enough of these to affect the big ecosystem, depending on how efficient these are. We wouldn't need to cover that much. If we're already covering, like I could imagine solar panels, or like the panels that are solar panels on top and like Earth thermal panels on the bottom, so you don't like it takes up the same amount of surface area of the Earth. You're not actually covering much more. But wouldn't that be so cool?
Yeah.
Which means there's definitely people lobbying to prevent it from happening.
Yeah. Good luck to the team in Sydney.
Yes.
Or whoever is still working, hopefully still working on this.
Yes. Good luck.
Project.
Good luck. Hey friends, it's me. Connie is out on the balcony overlooking the quad with our infrared binoculars, so I am going to take these few minutes to share some messages with you. The first message is a big thank you to all of the patrons who support the show financially every month. We are an independent podcast, so it would be really hard to make this podcast without your support, so thank you so much. And we want to say a huge thank you and a special shout out to our Sun-like stars, Scott Reynolds, Tom T., Nicole Bartlett, Ashley Shambo, and Bruce Sedloff. You are golden. Thank you so very much. If you want to support this indie podcast on Patreon, you can hear your name on the show like these awesome folks. You can make it onto the patron star chart and get research notes for most episodes for $5 a month at patreon.com/palebluepod. You can also make a one-time donation and become a supernova in the Pale Blue Pod sky. That's at the PayPal link in the episode description if a monthly donation isn't for you. And of course, if you can't support the show financially right now, we completely understand. There are other ways to help the show out. If you rate and review us on whatever podcast app you use, that goes a long way. And word of mouth recommendations are very powerful, very effective at helping shows grow. So if you take a link to an episode you love and send it to someone who you think would also love it, that would be fantastic. Connie and I would be eternally grateful. But of course, no matter what you do, thank you just for listening to the show. Connie and I are honored to be a part of your week. My next message is a podcast recommendation. It's another show in the Multitude Collective called American Medieval. It's a podcast about the Middle Ages, but with an American twist. Every week, Professor Matthew Gabriel is joined by an expert scholar to talk about either some bit of the medieval world itself or how Americans have, throughout our history, used the Middle Ages to say something about ourselves. If America has never been fully modern, it might be because we've always been a little bit medieval. So check out American Medieval every Wednesday. That's when new episodes come out. And you can find them at americanmedieval.com. Or if you don't want to take a spelling test, you can head on down to the link in the episode description. Okay, Connie is back. Apparently, she watched some students play a game of anti-gravity hacky sack, but we are going to get back to this conversation, and we have a fun game prepared for you. Want to play a game?
Sure. This makes things make more sense. There's a text you sent me earlier, and now it makes sense.
You want to tell them what text I sent you earlier?
Moiya asked me, a straight person, what women I find attractive, and I had to think about the answer. And I'm curious. I haven't scrolled down yet to see
don't scroll.
who made the list.
Okay, we are going to play Some Like It Hot, where I give you an Earth candidate and a space candidate, and you have to tell me which one you think is hotter.
Okay.
Okay. Don't scroll too far, though.
I haven't.
Okay.
I haven't. I see the first two options, and that's it. And the second one is rude.
Sorry. That's because I know you well. Sorry. Okay, first round of 5 in Some Like It Hot. You have to choose which is hotter, Morris Chestnut or the black hole at the center of M87.
I'm gonna go with the black hole.
You think it might be
it might be a generational thing. Like he's objectively attractive, but like not for me. I think. Well, that's not true. I'm thinking about. Anyway,
right?
Yeah,
like, look at that face.
Yeah.
Look at those cheekbones.
Yeah, it's not fair. But I'm gonna go with the black hole on this one.
Okay, you are correct. The image was taken in 2019 with the Event Horizon Telescope. It was the first black hole picture we ever took. Although really what you're seeing illuminated in this is not the black hole itself. That's that empty spot in the middle.
Yeah.
But you see this red and orange kind of swirling donut around the central black hole. That's the accretion disk around the black hole of material that's falling into it. And the event horizon is that boundary right at the edge of the black hole between it and the accretion disk. So the black hole's temperature is technically like 0 or like very close to 0 because it's not emitting energy. But the accretion disk around it is quite hot. That's about 1 million degrees Kelvin. This is for a very massive black hole. If the black hole at the center of our galaxy is about 4 million times the mass of our sun, the black hole at the center of M87 is about 2.5 billion times the mass of our sun. Still kind of minor leagues for supermassive black holes, but much bigger than ours.
Oh.
And it's about 55 million light years away. But yes, millions of degrees is hotter than Morris Chestnut, who is about 300 degrees Kelvin.
Is that 98.6 in K? Yeah.
Roughly, yeah.
Got it. Okay.
Great job, bestie. Second, who is hotter, Winston Duke or the Pillars of Creation?
Now, the Pillars of Creation are gorgeous. But I'm gonna go with Winston Duke on this one, actually.
Ding, ding, ding! You are correct.
And honestly, in the picture, it's very blue. It's very blue and green. So, like, I can see. I feel like I see there's reds in it. So, like, we can still use the infrared to study something as cool as the Pillars of Creation.
Oh,
because we can use it for anything, right?
Yes, but you are talking about the colors in this image, and I have to warn you that is not a very straightforward thing. I don't know what the artist who took the data and turned it into this beautiful image did to represent different wavelengths of light.
Yeah. I had that question, I guess, about the black hole, too. Like, we see it in this image as red. Is that, do you know, like, I guess it depends on who's making it to determine if the colors align to some sort of, like, how do they decide what colors?
It varies less within subfields of astronomy than it does between fields. But in the black hole image, it's mostly shining in the X-ray and UV. These accretion disks at millions of degrees, those are very high energy. So you're mostly talking about optical and above in terms of energy. So the red is not to tell you that it's infrared.
Okay.
In the Pillars of Creation image, the blue is also not to tell you necessarily that that's cold. I don't even think this is infrared data, but I can tell you that the Pillars of Creation are a part of the Eagle Nebula. So it's this big cloud of gas in the space between stars, and that interstellar gas tends to be very cold, around 10 to 40 degrees Kelvin, although you can see clearly that there are some stars in this image which will be millions of degrees, but the pillars themselves, the gassy parts, that's 10 to 40 Kelvin, or about negative 400 degrees Fahrenheit. So Winston Duke is in fact hotter than the Pillars of Creation.
Nice.
Yeah. Okay. Number 3. Please tell me who is hotter, Megan Thee Stallion or the crab pulsar?
I feel like it has to be Megan Thee Stallion.
Ding, 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 ding.
I feel like there was just like a no-brainer. But just because of Megan Thee Stallion, not because I know anything about the crab pulsar.
Because look at this picture.
I know.
Did I spend 20 minutes looking at pictures of Megan Thee Stallion to choose one to put into the notes for you?
Oh,
yes.
no. What a burden. What a tough time you had making the agenda for this episode. Wow. What
I'm a selfless
hero
queen.
You are. Absolutely. I know you did it for me, for my educational benefit. Yeah. And I appreciate you for that.
Thank you, bestie. And you're welcome.
Sacrifices you make.
You 100% got it right. The crab pulsar is an example of a neutron star. These are the remnants of energetic explosions, like supernova explosions, that came from stars that weren't quite massive enough to become black holes. But neutron stars are the second densest objects in the universe. This one is about 20 miles across, but around the mass of the sun.
Oh.
Yes.
Oh.
Very dense.
Whoa.
Very dense. And this one, they spin very quickly. That's for a neutron star to be a pulsar, it has to spin very quickly. And as it's spinning, much like a lighthouse, this beam of light that it's shooting out will come into our field of view at a very regular period. Some of them spin like once a second. This one spins 30 times a second, which is not... Like, there are millisecond pulsars. There are pulsars that spin hundreds of times per second. The surface temperatures of these neutron stars are about 1 million degrees. And yet, Megan Thee Stallion is, in scientific fact, hotter than the crab pulsar.
Wow. What's your rubric for this?
My eyes.
Gotcha. It was an optical observation. Okay.
I am an astronomer. We are experts at analyzing things with visual data. And my expert eyes tell me that she is hotter.
Got it. Science has said so.
Yeah.
This is just pure science,
This is just pure fact. Number 4. Please tell me who is hotter, Manny Jacinto or Saturn's moon Titan?
That one's really it's Manny Jacinto. But Saturn's moon Titan, 1, in this picture, looks so cute. But 2, I know that Saturn is real far from the sun.
Saturn is real far from the sun. Does it change your answer if I tell you that Titan is the moon with the thickest atmosphere in our solar system and the only moon with liquid oceans on its surface? Liquid lakes.
Of course it does. Let's see. Yes, it does, because liquid lakes means that it is warm enough for the water to be liquid, because under the atmosphere, which traps gases and heat,
atmospheres can do that. Yeah.
They can, but does it on Saturn's moon Titan?
That is the question here.
Oh.
Who's hotter?
Well, I'm gonna go back with Manny Jacinto.
Ding, ding, ding. You're 4 for 4, bestie. 4 for 4. Yeah, even though it has the thickest atmosphere, and even though it has liquid oceans and lakes and rivers, they are not liquid water oceans and lakes and rivers. They are liquid methane and ethane.
Yeah.
Yes.
I was thinking about that from our episode like a few weeks ago. We were talking about mini Neptunes and how there was liquid gas, and I'm still a little traumatized from that. So I should have thought about it. I did think it was in the back of my mind, but I thought the atmosphere,
the slushy fluid gas.
The atmosphere though was I was like, oh well, maybe. But then if it was liquid water, that would be a really big deal. We would have made a really big deal about that, because that's kind of what we've been looking for. Yeah. So you almost had me. And you kind of did, but you didn't.
Yes, you trusted your initial instincts, and I'm glad you did, because that atmosphere is not necessarily a greenhouse atmosphere. It's not the best at trapping heat. Titan doesn't have the best internal heating mechanisms, and methane and ethane don't need to be very warm to be liquid. But this is interesting because it's the only moon with a liquid cycle. It has rain, it has clouds, it has standing bodies and running bodies. So very cool. We are going to send the Dragonfly mission to study the atmosphere of Titan, hopefully in the next 10 years. It will launch, and its surface temperature is about minus 180 degrees Fahrenheit. So yes, indeed, cooler than Manny Jacinto.
Yeah. Just negative 179. With the other numbers we've been working with, that seems like a paltry number. It's like just a cool little 179. We were talking about like negative Kelvin.
I tried to get a range. Well, you can't do negative Kelvin.
Gotcha. Right. I think I did know that. But is it absolute zero? Is that the thing?
Yes.
Okay. I remember stuff. Yeah.
So proud of you. Are you ready for our fifth and final?
I don't know if I am. I know that there's no picture, but I saw that there were words, and I didn't fully read it, but you're probably diabolical.
Bestie, which is hotter? A morally gray fictional character with bulging biceps saying, "Who did this to you?" Or the universe immediately following the Big Bang.
Oh, no. So I do see there's a little hint here. It says 1E32K, and I'm gonna get there's an E in there, and I'm like, I thought I was gonna know what that meant, but
I've actually started writing my notes in more intense scientific notation because I know you're reading them.
But only like just ahead, so it's like you can still get me. But I was like, is there an exponent? So it's like 1 to the 32nd Kelvin. That doesn't make sense, but it might be that. But to me, a morally gray fictional character with bulging biceps who's saying, "Who did this to you?" While you're like maybe pressed against a wall, you've just had a harrowing experience, and you're still shaken up, but then the protector is here, and you're against the wall. Maybe it's raining really intensely outside, like it's thundering and lightning, and like there's a fireplace going in the side, and just like, who did this to you? Come on, that's more than one E32K.
Like, cause I you know how I know that's hotter? So that notation 1E32 is 10 to the 32nd power.
Okay,
I know for a fact if I was in that scenario, I would melt. So I know that that is hot enough to melt human flesh and bone.
Absolutely.
Bestie, you went 5 for 5. Congratulations.
Diabolical game, though. Diabolical game.
Thanks. I feel like it was also diabolical to put it in the middle of the episode as opposed to the end, but I just knew we would need a palate cleanser after talking about Earth stuff.
Okay.
And I thought it was a nice bridge from Earth to space, because now we can talk about the space uses and like major discoveries for infrared light.
Okay.
I think that one of the coolest things about infrared light in terms of astronomical observation is that because infrared light doesn't get scattered like visible light does when it interacts with dust particles, we can see the infrared light more intact as it's passing through dust. So we can see how dust is distributed, which is important because there's a lot of dust in the universe. And it's not very hot. Like, a lot of it is really cold, so we can't study it with other wavelengths of light unless it's like absorbing energy from a star or something. But at some wavelengths of infrared light, we can kind of start to peer through it, especially the longer wavelengths. So then you can start to study stars inside of nebulae, inside of gas clouds, which is really cool. So that's why we can study things like pulsars that are like the Crab pulsar. We can study that in the infrared, and it's in the Crab nebula, so there's a lot of gas and dust around it.
Right.
But
okay.
This is why we need these longer wavelength observations. It also lets us study cooler objects like things that don't quite become stars. So brown dwarfs, protostars. These are, eventually they will become stars, but they haven't started fusing yet because gravity is still collapsing them and they just aren't as hot yet. So they shine more in the infrared than they do in the optical or UV. They're really good for early universe sources. Have we talked about the cosmic microwave background?
Yes, and scientists thought it was bird poop.
Yes, of course. So the cosmic microwave background, that signal was initially released in the optical or in the ultraviolet. It was initially a higher energy burst. And then as the universe expanded, that light also got stretched through something called cosmological redshift. So it went from being in the optical or the ultraviolet into the microwave. Other things have done that too. And so slightly younger objects, the galaxies that formed like 400 million years after the Big Bang instead of 400,000 years after the Big Bang, they haven't shifted all the way into the microwave, but they will have shifted into the infrared. So we can study early universe galaxies, early star formation with infrared light.
Nice.
And exoplanets,
Your
which
favorite thing.
we all know is my favorite thing. Yes, we can use infrared to directly image exoplanets. That's how we can get to them because they don't shine on their own,
right?
But they will absorb heat from their stars and then re-emit them. So directly imaged planets are often done in the infrared.
They don't shine on their own, but they have Beyonce as a protector.
Good job, bestie. Loved it. Yeah. Good for them. I hope they know that.
I hope they do.
We can also study their atmospheres with infrared light. As light from the star passes through the atmosphere, maybe gets absorbed, then gets re-emitted, and then we can study maybe as the planet is like not directly in front of its star, but on its side, we can study the heat signature of its atmosphere if it's big enough, like for the puffy, hot Jupiters especially.
Right.
And we can do all of that with help from telescopes. And unlike...
Remember when I asked you for telescope recommendations?
Yes. Yeah, but these aren't telescopes you can buy.
Exactly. Like your range of telescope, it's like, of course they go all the way down to like the basics, but like whenever you're talking about a telescope, it is very different than when I'm thinking about a telescope.
Facts. So there are a few dedicated infrared telescopes. In my first research experience, used Herschel data. This was a European Space Agency telescope, but people all over the world can use its data. And it operated from 2009 to 2013. When it launched, it carried the largest telescope with a mirror about 3.5 meters across that had ever flown in space. It's been beat in size since, but at the time, very impressive. Its mission was to probe the formation of stars and galaxies and to study the physical and chemical properties of comets and asteroids in our own solar system. It had 2 cameras and a high-resolution spectrometer, and I have data from it tattooed on my leg.
Oh, you do?
Yes, I do. Sometimes people, when they see it, they think it's like the EKG, like the heart thing.
The graph. Mm-hmm.
The heart graph, yeah. But no, it's spectral data from a galaxy called IRAS 08339 plus 6517. That's not written in the notes. That number is burned into my brain.
Is it burned into your body? You didn't put that part.
No, because I actually am really disappointed in 19-year-old me because she didn't label the axes of the graphs in the tattoos. So I know that they're data from that one galaxy. I know that there are 3 graphs, and one of them is carbon, and one of them shows nitrogen, and one of them shows oxygen. I don't remember which is which.
Oh.
And I don't remember the wavelengths for them.
You know, when they say to be careful when you get tattoos, you know, just make sure you get the axes right. Like, that's a common one, you know, like, I don't know how you missed that one. It's what they say when you get tattoos. Make sure you label the axes.
It's what they say when you draw graphs in science class. Like, always label your axes,
You know?
always say what unit you're working with. And I failed. But I think, like, it's
symbolic.
Fine. It's symbolic, and it's like more artsy without the labels.
Yeah.
But if I really needed to, I could figure it out, and I could go back and label them.
Yeah.
It's just kind of fun not knowing.
Yeah. No, I love that.
Yeah.
It's like such a unique tattoo, too.
So it's an IRAS galaxy that's the data, but it was Herschel data of an IRAS galaxy. And IRAS is a completely different infrared mission. It stands for the Infrared Astronomical Satellite, and it was the first infrared space telescope, which is why its name is so basic.
Yeah. It's either a person or it's really basic.
Yes, especially back in 1983, like they were just starting out. They didn't have to wow anyone with the name because you know, the fact that they were going to space was enough to wow people. It only lasted 9 months, which is shorter than like any mission that we would launch into space today. But during those 9 months, it detected about 350,000 different infrared sources in the sky, including this galaxy on my leg. And it found new comets, and it found dust grains around distant stars, including Vega, which will one day be our North Star. And seeing dust grains around another star indicated that there would probably be planetary systems around other stars as well. This is back in the 80s, so then in the 90s, they could start finding exoplanets. And it was like big international collaboration between NASA, the Netherlands, and the UK.
Nice. We love international cooperation.
Yes, we do. Yes, we do. And IRAS was really kind of like the first test. It was the first pancake for infrared telescopes. The next generation was Spitzer, which operated from 2003 to 2020 and found a lot of objects in the infrared. It discovered a faint ring around Saturn that we didn't know about before, and we've since named it the Phoebe ring of Saturn.
Okay.
It was Spitzer that took the first direct image of an exoplanet, so thank you, Spitzer. And it's found water vapor in the atmospheres of exoplanets. After that, Hubble was before that, so this was a successor to Hubble, but this is like a precursor to JWST. I'd say Spitzer and the Hubble Space Telescope are probably like JWST's telescope parents.
Gotcha.
And then another one that I really want to talk about is the Japanese Akari spacecraft, operated from 2006 to 2011, and it was a collaboration between Japan's JAXA. I think they have a cooler name than NASA. It's their space agency, and Europe. Like that's what their website said. Europe, like who? All of them? I guess the European Space Agency is what I'm guessing.
Perhaps, yeah.
And then Korea, and the name Akari means light in Japanese, and it was designed to be an all-sky infrared survey. So over the course of its mission, take images of the entire sky in near, mid, and far infrared. It had a couple different cameras on it, and it was successful, as far as I know.
Nice.
So that's how we have collected infrared light. After hearing all of that, do you have any lingering questions about this part of the spectrum?
Not currently. I'm still processing the new information because, I think mostly of infrared as like, oh, I know it's how our remotes work. It's like I've heard of it probably more than, well, maybe not more than some of the other wavelengths, but like I've been aware of it, but I didn't quite realize some of its uses, obviously its history, although we did discuss some of it recently and I remembered. But yeah, it's very interesting because it helps you see things in the reverse of what you can see in the optical in space. Like that's probably not exactly, but like it is helpful for me it was helpful for me to like flip into that framing of like, okay, you can see all these things in the optical, but it helps you see all the like it just feels like a reverse image, which works really well for the light and photography connection there. So that's cool.
Yeah, it's a really great way of thinking about it. The reverse image, like the negative image.
Yeah.
Nice. Yeah. Well, we've now covered UV and IR. Mm-hmm. What do you want to cover next? The next time we do a light topic.
Yeah. Let's get into the microwave.
Okay, we're going to keep going in this direction, getting longer wavelengths. Okay.
Sure.
You don't want to bounce back and forth?
No. I think we can go in order. Are we?
We're going in increasing wavelength order.
Okay. Yeah. It's just the one you mentioned, last in my mind. You did also mention optical today, but microwave will be will be good.
Okay, then we'll do microwaves not next week, but the next time we do an electromagnetic spectrum episode. It'll be about microwaves, so that's exciting. And until then, you are hot and you are space.
Yeah.
Bye.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm at ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.